Okay, hi everyone. This is going to be a video lesson about exponential functions for pre-calculus. And since this is our first video lesson, I'll just tell you real quickly how it's going to work. Basically, at the beginning of each video, I'll try to do a quick introduction like this, and then in a minute or so, I'll switch over to my document camera, which you can't really see. It's right off the edge of the camera right now. But I'll switch to my document camera. It's kind of like a projector, and then I'll be writing notes. And hopefully it looks a little bit something like a whiteboard. You know, I'll be writing notes, you can take notes, and hopefully it'll feel like a normal class. So, exponential functions, what is this going to be about? It might sound familiar to you because you may have seen this topic already in an algebra class. And if you have, that's good. It's always good to get a refresher on this. But the following sections that we're going to do, we're going to talk about exponential functions, we're going to talk about logarithmic functions and equations involving them. And we do cover that sometimes in algebra classes before this, but it's kind of a tricky topic, so we like to cover it in algebra classes and then again in pre-calculus to make sure that everybody is on the same page. All right, so let's go ahead and get started. All right, so exponential functions. I actually would like to quickly do a quick review of exponents. Now, this quick review of exponents will probably take about 1 page or maybe a little bit more than a page. And technically, it's not really in the topic of exponential functions, but I think we should spend about 1 page reviewing exponents just to remind ourselves how these things work. So, first of all, when we write a to the b, okay, a to the b, what does that mean? Well, we call b an exponent, and we mean that a to the b is a times a times a times a times a. How many times? Well, the number of times that a needs to appear is b times. And you know that sometimes we call an exponent a power. And there's also some other details to this. Like, it looks like when I write it this way, I'm kind of assuming that b is a positive integer. And if b is not a positive integer, then that's something that we'll have to talk about when we get to it. But some quick examples. These are not really example problems yet. These are just some quick examples of exponents. So 2 to the 3. If you see 2 to the 3, you know that that means 2 times 2 times 2. I knew how many times to write 2. I wrote it 3 times. We could do 2 times 2 times 2 in our head. You don't need a calculator for these kinds of things. It's 8. We can also do something like 10 to the 5th. 10 times 10 times 10. We need 5 of them. You can also do this without a calculator. This is going to wind up being a 1 with 5 zeros. All right, so those are some quick examples of exponents. Now, I'd like to talk about some properties of exponents. Some properties, or you could call these rules of exponents. All right, so we're going to have a list. We don't really have to... it's not so much about memorizing these. It's just about getting used to the way that they act. So a to the m, a to the n, when you see something like that, it means you can just add the exponents together. If you had something like a to the m over a to the n, where there's division involved, that's going to be a to the m minus n. You take the exponent on top and you subtract the exponent on the bottom. Another property is that a to the 0 If I did something like 5 to the 0, or 4 to the 0, or 10 to the 0, whatever it is, it's always going to equal 1. Another property is for negative exponents. If you had a to the negative n, that's the same as 1 over a to the positive n. Property 5 is about how parentheses work. So if you had a, b in parentheses and it's raised to the n, that's the same as a to the n, b to the n. It's kind of like you can distribute the power across the parentheses and just raise each part to the power. I'm going to continue the list up here. I think this list is going to go up to 9 things. So property 6. Property 6 also involves parentheses. It's a to the m raised to the n. So this looks like we're doing a to the m first, right? Typically with parentheses, you do the part in parentheses first. And then you would do the part on the outside. This property is going to say that that actually equals a to the mn. So it's okay to just multiply m times n and get one exponent out of it. So if you're raising to the 2 and then you're raising to the 3, you could just raise to the 6. Gets the same result. We have one with parentheses and a fraction. So if you had a over b to the n, this is going to equal a to the n over b to the n. So this just says that you do the numerator raised to the power and the denominator raised to the power, which is good. A lot of these are kind of saying that exponents sort of behave the way that we would expect them to. You know, this is a nice property to have. Just says, just do the numerator to the power and the denominator to the power. Number 8 says if you have a to the 1 over n, I guess this is assuming n is not 0, you get the nth root of a. And the most common root that we deal with in this class is probably the square root. So a to the 1/2 would be the square root of a. But you could also have something like a cube root, fourth root, something like that. All right, and then property 9 is if you have a raised to the m over n, that is the same as doing the nth root of a to the m, and that is the same as doing the nth root of a to the m. All three of these things are equal to each other. And I'll show you a couple of quick examples. I don't think we're going to necessarily see examples of all 9 of these. Let's do some quick problems. We just want to get used to working with exponents again. So here's an example problem. It's going to say simplify. It's going to have a part A and a part B. So part A is 27 to the 2/3, and part B is the 4th root of 81 over 16. All right, and we're not going to use calculators much, so let's do this without a calculator. 27 to the 2/3. This is not, it doesn't have to just be a mystery to us that we plug into a calculator and get some answer. We can do this by hand if we understand how exponents work. All right, so first of all, I'm thinking we're raising something to a fraction. That kind of looks like property 9. Property 9 has 2 different things on the right-hand side. You know, I could use the middle one or I could use the right one, and I could say which one of those looks more convenient to me. If I use the middle one, then I guess I would be doing the 3rd root of 27 and then raising it to the 2. That sounds good. Let's try that. The 3rd root of 27, parentheses, raising it to the 2. The reason why I said that looks good is because we can do the cube root of 27 by hand. Remember, the cube root of something means what number would you have to multiply by itself 3 times to get 27? All right, so I want something times itself equals 27. It's going to be 3. Because 3 cubed is 27. 3 times 3 times 3 is 27. Oh, and look how much we simplified it. Now it's just 3 squared. 3 squared is also known as 9. So there's the answer. So 27 to the 2/3 turns out to be 9. For part B, I think I'm going to use, let's see, well, we have a root here, and I know that the 4th root of something could be thought of as raising to the 1/4. So maybe I could think of this as let's write that. Let's just write that. 81 over 16 to the 1/4. You know, I guess that's by property 8. And now I'm looking at it and I'm thinking property 7 looks useful. Here, I'll write some of this. We did this by property 8, and now I think I'm going to use property 7. Sometimes you have to use a combination of these. And that says that we could do 81 to the 1/4 and 16 to the 1/4. So let's write that. 81 to the 1/4 over 16 to the 1/4. Is that really any simpler, though? It doesn't look like it's any simpler. If anything, it might even look a little more complicated. Maybe what I'll do now is turn it back into terms of the 4th root and say this is the 4th root of 81 over the 4th root of 16. Now, I think this is something we can work with, because we could just try to figure out what is the numerator, and try to figure out what is the denominator, and think of them as 2 separate little problems. For the numerator, I want to find the 4th root of 81, so that would be a number that when I raise it to the 4th, it gives me 81. In other words, a number that if I multiply it times itself 4 times, I get 81. And we try to think of, small integers that might work out. Does 2 work? Does 3 work? Does 4 work? If we're lucky, then it turns out to be an integer. And yeah, this turns out to be 3. Because 3 times 3 times 3 times 3 equals 81. And on the bottom, I need a number that when I raise it to the 4th, I get 16, and that turns out to be 2. So I'm going to write underneath this, in case anybody doesn't see that, it is because 3 times 3 times 3 times 3 is 81. And 2 times 2 times 2 times 2 is 16. So we can do these kinds of things in our head as long as they work out, as long as the problems are kind of designed for us to do without a calculator. We don't have any weird decimals showing up or anything. So that was one page of what I'm calling a quick review of exponents. Just what exponents are and a few properties of them. And that's going to help us going forward. Now we can really get to the topic that we want to talk about, which is exponential functions. So let's move this page up a bit. Try to keep it there a little bit. It's kind of tricky to fit everything on my desk, but I'll do my best. So now we want to actually talk about exponential functions, because there were no functions in the discussion above. So definition. Definition. So given a number a that's greater than 0, and the number a is not equal to 1, the exponential function with base a is f of x equals a to the x. And this is kind of like two definitions in one, because it's a definition for the phrase exponential function, but it's also telling us about this word base. The number a is going to be referred to as the base of the exponential function. And it says that the base needs to be positive and not equal to 1. I'll tell you real quick the reason why we have those requirements. First of all, if a were allowed to be 0, that wouldn't be a very interesting function. If a were allowed to be negative, it actually would be a pretty interesting function, but it's just kind of its own thing that gets talked about separately. It's not a part of this discussion of exponential functions. For exponential functions, it's just positive. And I'll say that if a were equal to 1, then this would not be a very interesting function. So that's why we have that requirement. All right. Right away, I'd like to say, note, this is not to be confused with x to the a. A to the x and x to the a are very different from each other. How different are they? Let's do a little example, a little discussion. All right, example, let's let f of x equal 2 to the x, and let's have another function that is x to the 2, because I want to show you how different these are. 2 to the x is an exponential function with a base of 2. The other one, x to the 2, I mean, we would call that a polynomial. In particular, we would call it a quadratic function. It's a parabola, right? Anyway, what I want to show you is, to show you how different these are, what do we get if we do f of 30? And what do we get if we do g of 30? So if we do f of 30, then we're doing 2 to the 30th. And if we do g of 30, we're doing 30 to the 2. All right, let's do the easy one first. Which one do you think is the easy one? I think the second one is the easy one. 30 squared, I could do that in my head. 30 times 30 is 900. Now 2 to the 30th. 2 to the 30th I can't really do in my head, because it's 2 times 2 times 2 times 2 a bunch of times. This actually turns out to be a gigantic number. It actually turns out to be, and I did use a calculator for this. Let's see. Turns out to be this number, which is a little bit more than 1 billion. 1,073,741,824. So that's very different from 900. And, this came from us putting in x equals 30, and 30 is not even that big of a number. 30 is a, medium-sized number. And we get a gigantic thing from 2 to the 30th. So a key idea to remember here is that exponential functions grow much faster than polynomials. But for now, it was just to show you that x to the a and a to the x are drastically different from each other. Now, let's focus in on the exponential functions, and let's talk quickly about the domain. Domain of exponential functions. I'm going to tell it to you for now, and if we have time later, we might come back and discuss this a little bit more, but it's actually the set of all real numbers. Fancy looking R means the set of all real numbers, meaning that we could put in any value of x we want. If you have a to the x, x could be negative, x could be 0, x could be positive, anything you want. I'm not really proving that to you right now. We're just sort of stating it. We'll come back and talk about it more later if we have time. By the way, this is also known as the interval from negative infinity to positive infinity. Okay. Now, in this class, or just in math classes in general, when we start talking about a type of function, we like to talk about domain, we like to talk about range, and we like to talk about graphs. So let's talk about the graphs of exponential functions. Now, the exact graph of an exponential function is going to depend on what is the base, right? So 2 to the x and 3 to the x and 4 to the x and 4.5 to the x. You know, different bases should have different graphs. So I can't show you all of them right now, but I'm going to show you that they fall into, broadly speaking, 2 different categories. And that's nice because we can just draw these 2 cases, 2 graphs, and discuss them. So let's have 2 different xy planes. And let's set this up on kind of roughly the same scale. I'm going to have a 1, 2, 1, 2, 1, 2, 1, 2. When you graph things, you should label some numbers on the x-axis and y-axis so that you could tell what the scale is. All right, so the first graph I'm going to show you is, in general, the graph of y equals a to the x when a is greater than 1. First of all, I know that a to the 0 is 1. Okay, that was one of those properties of exponents. A to the 0 is 1. That means that this graph must pass through the point 0, 1. So that's at least 1 point on the graph. We also know that it grows very rapidly. You could put in, a and a squared and so on. It's going to grow rapidly. Overall, the shape of this graph is going to look something like this. Keeping in mind that the exact graph depends on the exact value of a. This keeps going up and up and to the right. We said the domain is all real numbers, so you could put in a large value of x or a small value of x. Let's see, what can we say about this? Maybe I'll leave it at that for now, and let's talk about the other one. What is the other case going to be? Well, up above in the definition, we said that an exponential function has a base a, where a has to be positive and not equal to 1. Well, if this is case 1, where a is greater than 1, the only other case that we could have is that a is less than 1. But in particular, a has to be positive by definition. So this is the case for values of a between 0 and 1. This is like if you had a equals 1/2. 1/2 raised to the x, or 2/3 raised to the x. Something like that falls into this category. And the graph is actually going to look different in this case. First of all, I still know that a to the 0 is still going to be 1, so it's still going to pass through this point 0, 1. That hasn't changed. But what has changed is the overall shape of the graph is that if you imagine something like 1/2 to the x, you do 1/2 to the 1, 1/2 to the 2, 1/2 to the 3, it actually gets smaller as you go to the right and gets larger as you go to the left. It's going to look something like that. And these are, broadly speaking, the 2 cases of graphs of exponential functions. Depending on what a is, it's going to look something like this first one or something like the second one. It might go a little bit steeper or a little bit more shallow, but the overall shape is going to look something like this. Now, up above, we said the domain. So something else that we should address is what is the range in each of these cases. You know, the domain is basically what x values we're allowed to have, and the range is what y values we get out of this. So think about this for a second. What do you think, based on this graph, what do you think the range is? I guess something that maybe I could make a little bit clearer is that this line here, it's approaching the x-axis, but it never quite touches it. And the same thing is happening here. This line is going lower and lower and lower, approaching the x-axis, but never quite touches it. We have a name for that, right? That's actually an asymptote. Sometimes we draw asymptotes with a dashed line. So let's try to do that here. The actual exponential function approaches this dashed line, but never quite touches it. So the function never actually gets that low. It never gets down to 0, but it does have every y value greater than 0. Everything above 0. So the range is going to be 0 to infinity with a curved parentheses next to the 0. And that's the same in this case as well. And you know what? Let's just explicitly write out there is an asymptote at y equals 0 in both cases. So even though the graphs look different, they both have the same domain, they both have the same range, they both have the same asymptote, they both have the same y-intercept. And they have a very similar formula, a to the x. It's just that a to the x either falls into being greater than 1 or less than 1. Now, chances are you probably won't be asked just to draw a graph of like 2 to the x or 3 to the x or something like that, you know, but something that you might get asked is to draw a graph transformation of one of these. So let's look at graph transformations. Graph transformations are something that can be discussed, you know, previously in an algebra class. But I want to quickly remind you of, let's talk about at least four different transformations. What if you had a function and then you added a number to it, like plus c? I'm going to assume c is positive for the discussion we're having here. If you have y equals f of x, and then you add a constant to it, this is going to have the effect of shifting up c units, right? So y equals f of x is getting shifted upward because all the y coordinates are getting c added to them. If you had f of x minus c, then you're going to shift down c units. Some other ones that you could see is, what if the plus c or the minus c is on the inside? So y equals f of x plus c, or y equals f of x minus c. These also shift the picture around on the xy plane. Sometimes these feel a little bit backwards to me, but this actually is a shift left c units. And this is actually a shift right. And if that seems a little bit backwards to you, you can actually set up a little table of values. Like if you ever are doing that kind of transformation, you could set up a little table of values to convince yourself whether it needs to be moving left or right. All right, I said we were going to look at least 4 of them. Actually, let's look at 2 more. What if you have a minus sign out front? What does that do to a graph? Like the graph of y equals f of x now has a minus sign out front. Well, all the y values are going to get flipped. So this is going to reflect across the x-axis. In other words, this is a vertical flip. X-axis. Why am I saying x-axis? Well, think about if you were to take something and flip it vertically. Let's look at these pictures again. Like if I wanted to take this first picture and flip it vertically, we would flip it across the x-axis. And we're using the word reflect because you could almost think of the x-axis as like a mirror. And you want the mirror image of this graph reflected across the x-axis. It's a vertical flip, even though you're moving across the x-axis. And then the other one would be if the minus sign was on the inside, and that is going to have the effect of reflecting across the y-axis. That's a horizontal flip. In that case, the y-axis is kind of acting like a mirror, and you're trying to get the mirror image, so it's flipping horizontally. And we can also combine these. We could have a graph that's shifted up or down, left or right, maybe flipped vertically, all of that happening together. So I'll show you an example problem. Here's one type of thing that you could get asked. Is let's graph f of x equals 2 to the x plus 3 minus 1. So you could get asked to graph this, or maybe you could be given some pictures of graphs and be asked to identify which graph goes with which function. So you need to understand how these transformations are working. I would say this looks like 2 to the x. So let's start with the graph of y equals 2 to the x. That's an exponential function with a base of 2, and it's going to look like case 1 in those two cases that we drew a few minutes ago. And then think about what's happening with this plus 3 and this minus 1. Well, the plus 3 is up there in the exponent, so that should be happening first by order of operations. The plus 3 is attached to the x like this. It's x plus c, right? It's kind of like we have an x plus 3. So it's going to shift left 3 units. Let's write some of this. We're going to shift left 3. And then what about this minus 1? The minus 1 is on the outside, and that kind of looks like this second one here. This is like we have a function, and then there's a minus a positive number on the outside. That's going to shift the picture down. Down 1. So if we start with a graph of y equals 2 to the x, and we shift it left 3 and down 1, then we'll have a good answer. So I'm going to draw 2 pictures in order to solve this. I'm going to start with a picture of 2 to the x. Which is actually not going to be my final answer, but, I think we should draw this to start it out, and then we'll shift it appropriately. So 2 to the x, we know from the previous page generally what it looks like. We know it has an asymptote here. Let's go ahead and try to make like a dashed line. And we know where the y-intercept is. But now we have a specific value of a. We have 2 to the x. So we could draw this more specifically than what we had before. We could actually have specific points. For example, when you put in x equals 1, you're going to have 2 to the 1. That's 2. When you put in x equals 2, just to be clear here, what I'm trying to draw is the graph of y equals 2 to the x. Right? So if I put in 0, I get 1. If I put in x equals 1, I get 2. If I put in x equals 2, I get 2 to the 2, which is 4. All right, that's probably enough to get like a good graph because we know the overall shape of it goes like this. So we have the correct overall shape, and we're passing through a couple of good points. And now we want to apply the graph transformations. We want to take that picture and shift it to the left 3 and down 1. And we could do that in 2 separate steps if we want, or we could do that at the same time. Shifting left 3 and down 1. Why don't we just do them at the same time? So this second picture is going to be my final answer, so I'll try to make this a nice picture. Let's see. If we took that first picture and shifted everything to the left 3, well, you know what? How about this? The 3 points that we labeled, we could take those 3 points and move them to the left 3 and down 1. So like the point that was here gets moved left 3, down 1, and now it's over here. The point that was at 1, 2, shift it left 3 and down 1. It's going to be here. And the point that was at 2, 4, move it 1, 2, 3, and down 1. It's going to be here. That's why it helped to have 2 or 3 good points on the graph. So I'm imagining we need the same overall shape. We can draw that in. I think something else I'd like to do to make sure that this picture turns out well is let's draw the asymptote. The asymptote was at y = 0, but when you shift the picture down, the asymptote gets shifted down as well. It actually doesn't matter that this asymptote got shifted left, but it does matter that this asymptote got shifted down. So, okay, when I draw the curve, I'm going to try to approach this dashed line, but not quite touch it. And that's a good picture. That is a good graph of f of x equals 2 to the x plus 3 minus 1. I want to put a box around that or something. How about this? This question did not really ask us for anything else, but I'm going to say a few things about this function. I'm going to say, what's the domain? What's the range? And what's the asymptote? This is kind of like a follow-up question, you know, in case you were asked these things. So we started with an exponential function. We shifted it left 3 and down 1. The domain is still going to be all real numbers. That has not changed. Okay, or you could use the fancy-looking R for all real numbers. But the range has changed. You know, when everything got shifted down, the instead of having the range of 0 to infinity, we now have some points that go lower than 0. They almost get as low as the asymptote. They almost get as low as -1. So the range is going to now be -1 to infinity with curved parentheses. And the asymptote is now at y = -1, 1 unit lower than where it started. All right, how about this? I'm going to give you a similar problem to try. I'm going to ask you to try to graph something. And in these video lessons, when I have a problem that I would like you to try, you know, if we were doing this in person, I would probably just give you a few minutes, Maybe I would walk around the room and see how things are going. But because this is a video lesson, what I'm going to suggest is now would be a good time to pause the video, try this problem for a couple of minutes, and then you can hit play and we'll talk about it. All right, so we want to graph f of x equals -3 to the negative x. I think that it would be smart for us to start by thinking of this as 3 to the x, and then think about what graph transformations are happening here. The negative x, the negative in front of the x is going to mean that we want to reflect across the y-axis or flip horizontally. And the negative sign that's out front here is going to mean that we want to reflect across the x-axis or flip vertically. So we actually want to flip in both directions. Let's see if we can do that. So first we'll draw y equals 3 to the x, and then we'll deal with the flipping. This still falls into that case 1. This first picture doesn't really have to be exact because the second picture is going to be the final answer. All right, I think that on this scale, I could at least do the y-intercept of 1, and I could at least show that there's a point at 1, 3. I know that because 3 to the 1 is 3. The graph of y equals 3 to the x. And then we know the asymptote, and we know the overall shape of this thing. So based on those 2 points and the asymptote, we can draw this in. This is a little bit steeper than the 2 to the x was. Something like that. All right, now the transformations that we want to apply are that we want to flip horizontally and then flip vertically. But I think that we can do this in one step. If you want to do that in 2 steps, it's fine. 1, 2, 3. All right. How about this? The point that was at, like the 2 points that we kind of drew as dark points, let's figure out where they go. The point that was at 0, 1, here, it's kind of like over here. If I flip that horizontally, it doesn't really move anywhere. It's like it's already on the mirror. If I flip it vertically, it winds up down here. The other point that we had at 1, 3, if I flip that horizontally, it winds up here. And then I flip it vertically across the x-axis, it winds up down here. And I think seeing those 2 points helps me see what the overall shape of this thing needs to look like. The asymptote, if you flip the asymptote vertically and horizontally, it's still going to be here. We're not like rotating the asymptote or anything. We're just, you take that dashed line and flip it horizontally and flip it vertically. It's still in the same spot. But now the overall shape of the graph, it needs to pass through these 2 points. It also needs to approach the asymptote, but not quite touch it. So it's going to look something like this. Something like that. And this is a good graph of -3 to the negative x. Okay, so besides graphing, like what have we done so far in this video lesson? I guess we started with a quick review of some exponent rules, and then we talked about, what is an exponential function, which naturally led to us talking about what do exponential functions look like? What do their graphs look like? And then what can we do with graph transformations? So our next big question is, what are exponential functions used for? And it turns out that they're used for a lot of different things, but one of the most popular applications we like to show students first is interest. Interest on money, So exponential functions can be used in a variety of ways for this. So we're going to start with kind of a basic example. We're going to wind up with an interest formula that uses exponents. All right, I'm going to say, suppose a price starts at $100 and goes up 10% once per year. This would be a 10% interest rate, 10% annual interest rate. And I'm using simple numbers right now, but, we can imagine this as some amount of money. I started with $100, and I just called it a price. So, this could be a price of something that sells in a store, or it's just some amount of money. It could be an investment. It could be a loan. Whatever it is, we start with $100. And I want to talk about what happens after 1 year, 2 years, 3 years. So after the first year, for 12 months, that price has been $100. Now it needs to go up 10%. And I think we can see what it means to add 10% to this, right? I know what 10% of 100 is, and you can just add that to it. I'm going to write this with multiplication. I'm going to say that a way to raise something by 10% is to multiply it by 1.10. Right? If you want to raise something by 10%, you could multiply it by 1.10. Or you can multiply it by 1.1. You don't even really need that extra zero there. All right, so now the new price is $110. What happens at the end of the second year? So at the end of the second year, it's not going to be 120, right? That's not going to be the answer. It's not going to just go up another $10 because for the past 12 months, the price has been $110, and we need to go up 10% from this. So what I'm going to do is take this 110, and multiply this by 1.10 to make sure that this goes up 10% of itself, and that's going to get me an answer of 121. So at the end of the second year, the new price is $121. And you can see where we're going with this. We're going to go another year. After 3 years, what happens? Well, for the past 12 months, the price has been 121. We want to go up 10% of this. And a way that we could do that is take this 121 and multiply it by 1.10. This is going to get us 133 and 10 cents. So, it's not just going up $10 per year. The percentage depends on what the current value is. What if I asked you, what is the amount going to be after the nth year? Where n is some variable, it's some unknown. Maybe n might be something like 10. Maybe n is 20. We don't know. We're just being more general here. Well, we could think about what we did here to get each new number. We started with 100. We multiplied by 1.10. Then we multiplied by 1.10. Then we multiplied by 1.10. It seems like each year we just multiply by 1.1, right? So we could say start with 100 and multiply by 1.1 and multiply by 1.1 again, and just keep multiplying by 1.1 until you've done that a total of n times. Or maybe a nicer way to write this is with an exponent, to say start with 100 and multiply it by 1.1 raised to the n. And that's why exponents get used here. And that's why this is going to ultimately be an exponential function. And this little formula here does work. Like if you were to put in n equals 3, you would get $133.10. Put in n equals 2, you'd get 121. But this also works for larger ones, you know. And it's nice to have this formula because if I wanted to know what the amount is going to be after 10 years, this formula would let me figure that out without having to do year 4, 5, 6, 7, 8, 9. I could just go straight to year 10 by putting it into this formula. Now, that formula works if you're starting with $100 and your interest rate is 10% and it's going up once per year. But, you know, in math, we always like to generalize things. We're going to say in general. Like, what if you start with a different amount? What if the interest rate's different? What if the interest is being applied every month? You know, we want like a formula that covers all circumstances. So we call this compound interest, and it is calculated by, it's going to be a formula that, you know, is related to what we just did, but it's going to look a little more complicated because we want it to cover other circumstances. So we're going to write the formula, and then I'll tell you what all these letters mean. Capital P times 1 plus r over n raised to the nt. I'm going to put a box around that. And let's talk about what these letters mean. So A of t is going to be the amount after t years. Capital P stands for principal. So this is the principal is just another word that means the starting amount. So now we're thinking of like maybe you're making an investment or you're taking out a loan, and the word principal means what amount of money are you starting with. Lowercase r is the interest rate per year. I want to say something about interest rates. It needs to be adjusted because interest rates are typically a percentage. You know, 10% interest rate, 5% interest rate. So I'm going to say such as 0.10 for 10%, or 0.04 for 4%, etc. Interest rates typically given as a percentage, but when we put it into this formula, we'll typically put it in as a decimal. A couple of other things I need to tell you what they are. Maybe just one more thing is n. What is n? In this context, n is the number of times that interest is compounded per year. And compounded is just another word for applied. Like how many times is interest applied per year? The only other letter that I didn't specifically say what it means is t, but t was mentioned up here. T is the number of years. So a is a function of t, where t is a variable. We could look at a of 2, a of 3, a of 4, and we get the amount after 2 years, the amount after 3 years, and so on. So for example, quick little example of this. How about if the principal is, we'll start with small numbers again. If the principal is $100 and a 10% interest rate is compounded monthly, what is the amount after 3 years? Now, in this course, we're really going to try to not use calculators much, but this is kind of the one topic where sometimes we can't avoid it. If we're dealing with dollars and cents, and we're dealing with very specific decimals, then we might use a calculator for some homework problems here or some examples in class. So I know that I want to use this formula. I know that I want the amount after 3 years. So I want a of 3. I know the principal was 100. Let's just start putting things into the formula. 100, 1 plus. The interest rate is 0.1. You know, for 10%, you could write it as 0.10, or you could just write 0.1. N, the number of times that interest is compounded per year. This problem has the word monthly, so that means it's compounded 12 times per year. And then we need to raise this to the nt. N was 12, and t is 3, because it's 3 years. If we can figure out what this equals, then that will be the answer. But without a calculator, there's not a whole lot that we could do. We could figure out that 12 times 3 is 36, and then we could try to figure out what's in parentheses here, but we'd have some kind of decimal, 1 point something, raised to the 36. I did find this with a calculator, and this winds up being 134.82, where I rounded off to the nearest cent. I want to say a couple of things about this. That was a quick little problem. One thing I want to say is 12 times 3 is 36. So the exponent is 36. And earlier today, we said exponential functions grow really fast. And we did something like 2 to the 30th. Remember when we did 2 to the 30th and it was like over a billion? I just raised something to the 36, but what I got as a result was just an ordinary $134. It's not like $1 billion or anything like that. So why is that? Why can I raise something to the 36 and not get an enormous result? Well, the answer is because the quantity inside the parentheses here, the actual thing that's being raised to the 36, is very close to 1. It's 1 plus a small amount, right? Because this is 0.1 over 12. So this is a little bit bigger than 1. And you have something just a little bit bigger than 1, and you're raising it to a large exponent, and you wind up with kind of a medium-sized number as the result. I would also say that if we did get an answer that was like $1 billion, then I would say that doesn't seem right. You know, this is a word problem, so it's good to do a reality check. I would probably say that can't be right. If I start with $100, 3 years later, I'm not going to have $1 billion. So, you know, always try to make sure that the answer makes sense to you. It also wouldn't make sense if I got something that was less than 100. Another thing I wanted to say about this is that this amount, I think I'll just write this, is better than the 133 10 we found above. You know, in that first example where we started with $100 and we raised 10% each year, that was after 3 years we had 133.10. But now after 3 years we have 134.82. So why is this getting us more money? What's different? Well, the only thing that's different is that now the interest is being compounded monthly instead of once per year. And a key idea, something that I think is interesting and important, is that when interest is compounded more often, that results in more money. We just saw that happen because when the same principal was used and the same interest rate was used, if we compounded once per month, we got a larger result than if the interest was compounded once per year. Now, is this a good thing or a bad thing? It kind of depends on the context. It depends on, is this an investment that you're making? If this is an investment that you're making, then yeah, you want a larger amount of money. On the other hand, this could also represent like a loan that you took out. If this represents a loan that you took out, then you don't want it to be a larger amount of money. In general, you probably don't have a lot of control over how often the interest will be compounded. You might have more control in real life over what is the principal and what is the interest rate, and how many years are we talking about. Let's see. I'll give you a little problem like this. I think this is a quick problem. We did kind of use a calculator to finish it. Let me give you one like this. Example. An investment of $1,000 has an interest rate of 4%, compounded quarterly. How much money is there after 3 years? And I'm going to ask you, maybe pause the video and try this for a minute. And it's okay to use a calculator to get the final answer. All right, so there's not a whole lot to write for this, but I do want to show that we're putting this into that interest formula solution. First of all, just to get organized here, I'm going to write what all these things are. The principal was 1,000. The interest rate that we're using is 0.04. N, the number of times that interest is compounded per year. It said quarterly, so that's going to be 4 times per year. And T is 3, because it's asking us after 3 years. So A of 3 is what we're looking for. We put the principal first, and then 1 plus 0.04 over 4. And it's raised to the 4 times 3. I guess without a calculator, I could probably go one step further. Let's just do this one step before I bust out the calculator. 0.04 divided by 4. I just see that because they're both 4s, I'm thinking, oh, I could do that. I could do that in my head. Right, that's going to be 0.01. So actually, what's in parentheses is going to be this. And 4 times 3 is 12. So without a calculator, this is the furthest I could go. Maybe I'll kind of like sort of put a box around that, because if this was like a test where I wasn't allowed to use a calculator, then I guess that's as far as I would go. But if it's like a homework problem where it's okay to use a calculator, I did put this into a calculator, and I rounded off to the nearest cent, and I got $1,126.83, and we'll say that that is the final answer to the problem. I do a quick reality check. I say, does that make sense? We started with $1,000, normal looking interest rate, and 3 years has passed. I expect the amount to go up a little bit from the starting amount. So yeah, I think that that makes sense. One of the things I sometimes see from students in this section is calculator mistakes, or sometimes students round things off too much, or sometimes students round things off in like the middle of the problem or the beginning of the problem. Really, you don't want to round anything off until the very end when you're trying to get it in dollars and cents. Then it's okay to round it to the nearest cent. I think I had one more thing to talk about here. All right, this has turned out to be a longer video lesson than I was expecting, but it's good that we're covering a few different types of problems. We had some graphing problems, some interest problems, and I want to finish with another type of problem that you could see. Another type of problem. And let's see. This is going to say, suppose f of x equals c times a to the x, where a and c are positive constants. If the graph passes through the points 0, 3 and 2, 12, what are C and A? All right, this is a different looking problem, and I don't want to give this one away. I want you to try this, so I would suggest that you pause the video, spend a couple of minutes trying this, and then we'll talk about it. All right, so I hope that you really tried this on your own, even if it's a little bit different looking. We are given the general formula of what this function looks like, and we're given 2 points that it passes through. Right, so based on what we know, we can work with this. We could say, you remember earlier we said that every exponential function of the form a to the x passes through 0, 1? We said that earlier. And, in the examples we drew earlier, we always passed through that y-intercept. Well, I notice in this problem that it has a y-intercept of 3. Okay, so instead of passing through 0, 1, this is passing through 0, 3. That must have something to do with the c out front, because no matter what a is, we would expect a y-intercept of 1. It's c that's making us pass through a y-intercept of 3. In fact, I could think to myself, if we had a 2 out front, like 2 times a to the x, You don't necessarily have to write this. I'm just kind of explaining my thought process. If there was a 2 out front, then I would expect it to pass through 0, comma 2. If we had a 3 out front, I would expect that to pass through 0, comma 3. And that's exactly what we wanted, right? This graph does pass through 0, comma 3. So from this, that is my thought process. From that, I'm getting C is 3. That's half of the answer. We also want to find out what A is. So the function is f of x equals 3a to the x for some constant a. We still want to find out what a is. We haven't used the fact that this passes through 2, comma 12, so let's try to use that. Two comma 12. So if this passes through 2, comma 12, we could say, you know, y equals 3a to the x. We could say 12 equals 3a to the 2. I put in 2 for x and 12 for y. We can solve this for a. Divide both sides by 3. You get 4 equals a squared. And then we need to take the square root of both sides. Ordinarily, when you take the square root of both sides, you expect to get a plus or minus symbol, right? Like a equals plus or minus 2. But remember, the problem told us a and c are both positive. So I don't need to say plus or minus 2. I can just say a is 2. So the function is f of x equals 3 times 2 to the x. That was this mystery function. And you could check this. You know, I'll just say you could check that this passes through the 2 given points. Right, like, does this actually pass through 0, comma 3? Well, put in a 0 for x and see what you get. It does wind up being 3. Does this actually pass through 2, comma 12? Put in a 2 for x and make sure that this equals 12, and it'll check out. So that was just kind of a unique problem. You know, sometimes you'll get interesting little problems like this that don't necessarily fit into a template, but I'm glad that we talked about that one. So I think we are going to wrap things up here. Okay, hi, it's me again. So we're going to wrap things up here. And that's the end of our lesson on exponential functions for now. We're still going to see more about exponential functions in the next lesson because we need to talk about, some of you might be familiar with the natural exponential function, the number e. So that's going to be in the next video. And when we talk about that, we're also going to revisit interest, talk about interest a little bit more, because some of you might know that there's also a second interest formula that we didn't talk about today. So we'll talk about that in the next video. And I do want to finish this by just mentioning that there are also lots of other applications of exponential functions. Some of them we might see in this course, some of them we might not. They might show up in like a biology course or a chemistry course, business, engineering, you know, computer science. But basically, exponential functions are used for like population growth, radioactive decay, and sometimes they show up in some surprising places as well. Okay, so that's enough from me. So thanks for watching, and I will see you next time. Take care.